Welcome everybody, welcome at a session that we titled Well-Balanced Machining, the Key to Precision and Productivity. For a little hour we are going to talk about how to keep machining in a balanced shape, and we learn how that will lead us to precise machining and productive machining. As always, I'm not alone here, I'm together with my colleagues, my friends, that make this event possible, that take care of all the practicalities around it, and I have just the pleasure of making a presentation for you. To put things in perspective first, if we talk about balanced machining, what do we mean? And let me try to formulate a number of things which are important to understand where we are with certain situations. If we talk about machining, if we talk about the basis on which we select cutting tools, we select machining methods, we select cutting conditions, we handle issues and problems. For a long time, for a big number of years, we talked about what we could call intuition-based machining. Intuition-based machining is where we base our choices, our selections on intuition, on feeling, on experience, on expertise. It's the traditional way. It's how we did it for a lot of years, and more since it's difficult to say, but let's say since a couple of years, we try to make a jump, and I think we were rather successful in making a jump towards model-based machining. Model-based machining is where we use models, and may I remind you that a model is not a theory. A model is a description of something. A model describes reality, hopefully in the best possible way. Model-based machining is where we use physical models that describes machining processes, that gives us insight in what's going on, and based on those models we make our selections, our choices. We select cutting tools, cutting conditions, and so on and so forth. That's model-based machining, and I have a feeling that in general in the world today of machining, that's where we are. We on the one hand, we have still the intuition-based machining. We made a jump towards model-based machining, but to truly fully exploit all the possibilities of model-based machining, there is a step we need to take, and that I call it sensor-based machining. Sensor-based machining is that we collect a big number of data that we can use to fill up the models we have been creating, and that the models can be used in the most effective way. So model-based machining is only possible, really usable, when we have it combined with sensor-based machining. The end is what we all talk about, we hear about, everybody is discussing it, digital, data-driven machining. And one could say, okay, if I take my models and if I take my data I collected through measuring, and I put that in a digital environment, then I reach a level of digital data-driven machining. Today, we are going to talk about cutting forces, the mechanics of machining, the models we use in machining for that. And we will see here and there, as we describe the models, that there is a need for sensor-based situations also. By the way, talking about these different levels, perhaps interesting for you to know is that soon we launch a survey in social media, because we want to find out your ideas, what you think about all these things. And yeah, if you have a couple of minutes left, why not participating in it and yeah, giving us some feedback on how you feel about those things. Now, model-based machining, the basic model when we talk about machining is a model describing a machining process. Machining is a process where we have a cutting tool that we push through workpiece material, and we deform the workpiece material, and we deform it so much that the material is shorn off, and the shorn off material is evacuated under the form of ships. That's the overall, the general, the fundamental model we use to describe a machining process. Now, if we look at that as a model, there are quite a lot of phenomena we have to take into consideration. There is the mechanical side, there is the thermal side, the tribological side, and so on, and they all kind of link together in one way or another. But today I want to focus with you on the mechanical side, the mechanics of machining. And if we look to machining, and if I show it in a slightly different way, machining as a process, it's kind of a balance exercise. You have on the one hand the cutting tool you use and the support of the cutting tool, that means the machine tool and so on. And that cutting tool has a certain ability to carry loads. On the other hand, the machining process puts a tool in a situation where certain loads are going to act on the cutting tool also. And we need to find a balance. We want to have a well-balanced process so that the load-bearing capacity of the tool and the loads acting on a tool during the process are in balance. Because if there's no balance, there is trouble in paradise. You have to have that balance, both technical and economical. Today we concentrate mainly on the technical side, and if we want to describe the balance, we need to talk about, again, mechanics. There are forces acting during this process. There are thermal effects, tribological effects, chemical effects, and so on. Today, as I already said, we focus on the mechanical part of it. And if you solve the equation here, if you take all the variables that influence the loads that are going to act on a tool, and you combine that with all the variables, the elements that give a tool a possibility to carry load, and you try to solve the equation and bring balance, you want to know, of course, if you did a good exercise. And you want to control. You want to see, okay, what I did, is that good now? Did I create what I wanted to create, a well-balanced machining process? And for that, and here I'm going to touch slightly on the sensor-based machining, because to find out if you solve the equation right, there are two sources of information for you. One source is the people around the process. You know, people being perhaps the most crucial thing still today in a production shop where we want to reach the highest possible manufacturing excellence levels. People, they have a feeling for it. You remember intuition-based machining. They feel things. Was this good? Was this not so good? Was there balance? Was there unbalance? And a source for you is ask people. Ask them, how was it with the process? How did it go? What did you observe? Another source of information, a little bit less subjective, because if you ask people, it's always a bit subjective, you know. But a less subjective source of information for you are the tools which have been used in the process. Look at the tools. And what you see on the cutting edges, what you see on the cutting tools is going to tell you a story. It's going to tell you the story how it was during operation. And if you look at tools in a structured way, and there are systems for that, there are concepts for that. The one we work quite a lot with is what we call GTDA, Global Tool Deterioration Analysis, where in a standardized way we are evaluating tools after they have been used and see what we can learn from it to do better next time. Now, as we are talking about mechanics, the mechanics of machining, very quickly a few definitions. What is a force? And here I talk very, very general mechanics. This has nothing to do with machining in the first place. A force is defined as any influence that can change the position, speed, or state of an object. That's the physical definition of a force. In case of machining, we want to change the state of a workpiece. We want to deform the material, we want to shear it off. That means we have to apply a cutting force to achieve that. When we talk about forces, around the corner is also pressure. Pressure is a force per unit area. it's the same, yet it's not the same. It's connected to each other. But you have a force, and you have a force or a unified force per unit surface, which is called the pressure. Work, another thing we use in mechanics. Work is force multiplied by distance. If you apply a force on an object and you move it over a certain distance, work has been done. That's the definition of work. And to be able to do that, to be able to apply a force which is big enough to move an object over a certain distance, you need energy. And the source of energy can be multiple. That is not the discussion point here. But to do machining, we need a force. As the tool is moving through a workpiece work has been done. And to be able to do work, we need energy. We refer to it as the cutting energy, the energy needed to cut. So a cutting force now, because before the word force, work, energy, power, which is work per time unit. If you put cutting in front, you are fully into metal cutting. You have a cutting force, cutting work, cutting energy, and cutting power. Bear in mind that in the mechanical world, we always have action and reaction. The tool is going to put a force on a workpiece to deform the workpiece material, but the workpiece is going to push back. You have action and reaction. Never forget that. Later on, when we talk about vibrations, for instance, it's important to realize that a tool is vibrating because a workpiece is pushing back to the tool. Power, as I already said, is is energy per time unit. It's kind of concentrated energy. That are the basic definitions we are going to use throughout this presentation. Force, work, energy, power. Now, if we talk about cutting, the basic concept, the basic model we still use today is referred to as the Ernst and Merchant theory. Ernst and Merchant, already in the 40s, they were describing a machining process, as you see in the picture here, as a tool with a certain geometry. That tool is moving through workpiece material, is deforming the material in a so-called shear plane. And to overcome the strength of the material, in that shear plane is going to act a shear force. The deformed material under the form of a ship is gliding over the cutting tool, over the rake face. There is going to be a friction force there. And based on those two forces, the shear force and the friction force, Ernst and Merchant developed a whole way of thinking on how cutting forces develop during machining. The conclusion of it, without going into details of this theory, is that on a cutting tool there is acting a so-called cutting force and a feed force. And that cutting force and that feed force, represented here by the blue, respectively the red component in the picture, that is the basis of further thinking. So I have a cutting tool. To make it cut, I need to apply a cutting force and a feed force. And that kind of macro modeling, which we use still today, based on Ernst and Merchant, and be careful, also based on so-called oblique cutting. Oblique cutting is a situation where where a cutting edge is perpendicular to the feed direction. So we have to bear in mind later on, if we talk about these things, the macro modeling also somehow has to take into consideration a certain cutting geometry we use. And, very important, most of the things here we say further about this way of working, this model we are going to try to develop together, is based on empirical data. With other words, what I called a couple of minutes ago, sensor-based machining. Machining based on data. And that's an interesting thing, you know, because it means that the models were created based on data. And once we have the models, we need more data to make the models better. Which makes a very nice closed loop to this. Ernst and Merchant said there is a feed force and a cutting force, perpendicular to each other. The feed force is acting in the direction of the feed movement of the tool, while the cutting force is acting in the cutting direction of the tool. What we see in reality is, because real cutting is not really only oblique cutting, but we use also cutting where the cutting edge angles are not 90 degrees, that there is kind of a reactive force which we refer to as the passive force, the passive component. Why do we call it passive? Well, very simple, because there is normally no movement in that direction, and as there is no movement, there is no work and there is no energy needed for that cutting force. But there is something else I'm going to come back later on for that cutting force. The real cutting force, the physical cutting force working during machining is the yellow one. It's the three components added together. And that gives us the real cutting force. The cutting force we would measure if we measure in reality cutting forces. Now, that cutting force is influenced by workpiece materials we are going to see directly, is influenced by the cutting geometry. The workpiece materials, I think you can understand that. It's about, the harder the workpiece material, the more difficult to deform. And I want to deform it because that's machining. So harder workpiece materials demands higher cutting forces to be machined. The cutting geometry, sharper tools cut easier than less sharper tools. And cutting data and conditions, obviously, if you increase your cutting data, you need to push harder against more workpiece material, for instance, because you increase your depth of cut, to do actual machining. Cutting forces, that they exist, and remember, as the picture shows, it's always action and reaction. For me, it's the same what you take as a basis. Is it a cutting tool pushing against a workpiece, or is it a workpiece pushing back against a cutting tool? Whatever, the two are there. Later on, we are going to see, first I want to determine or to see what the variables are and how they impact on a cutting force, the red part here. Later we are going to focus on what is here still the black text. What are the consequences of the existence of cutting forces? What do we have to bear in mind? Now, if we talk about cutting forces, we have to be a little bit careful when we refer to cutting data. Because cutting data, automatically people will say, yeah, cutting data, of course there's the depth of cut, the feed and the cutting speed. Those we normally refer to as the technical cutting data. It's the cutting data which are used in the workshop, which are used by programmers. A tool needs to be used with a feed, a depth of cut and a cutting speed. Those things are, relevant for the workpiece. Technological cutting data, however, which are slightly different defined, are relevant for the functioning of the cutting edge. Physical cutting data are very closely to technological cutting data, but let me say the difference is the scale on which you look at things. Physical cutting data are relevant for the physics of the machining process, but for the sake of simplicity here, technological and physical cutting data, we consider the same thing. But what's the difference with technical cutting data? Well, it's mainly the feed and the depth of cut which are under the consideration here, because we talk about the depth of cut. And the depth of cut relates to, as the drawing shows here very nicely, you have depth of cut symbol AP, but the length of a cutting edge in contact with workpiece material for that depth of cut is called the width of cut, symbol B. You also have the feet, which is the movement of the tool along the workpiece in case of turning as shown here. But with that feet corresponds a certain thickness of material that needs to be deformed to be able to do machining, which is referred to as the ship thickness. Symbol H here in the drawing. Now, in case of a tool with a cutting edge angle of 90 degrees, the kappa here, feet and ship thickness are the same, and width of cut and depth of cut are the same. But the moment we have cutting edge angles which are different from 90 degrees, we are going to see differences between feet and ship thickness and depth of cut and width of cut. The model we are developing here refers or is originally made up for width of cut and ship thickness. So there we have to be a little bit careful when we apply it. The model is based on, as I already said, empirical data. We measure and we see what we observe. And measuring, what I mean is, we take a cutting process, we take a measuring tool to measure cutting forces, in this case cutting forces, and we measure the three components. And we start to play with variables, different materials, different feeds, different depth of cut, different tools, and we document what we measure. That's the basis. And the first gentleman who did that in a structured way was a certain Mr. Kinzel in Germany. I'm talking about beginning of the 50s of the previous year. And he measured hundreds, thousands, tens of thousands situations and always was measuring cutting forces. I started to a little bit big data analysis avant la lettre in the 50s already, looked at the data and tried to find out, what do I see? Do I see something in all this data? And he did. He saw that for a certain tool, sorry for this, but I have a big cold, you know. For a certain tool in a certain workpiece material, if he started to play with cutting conditions and measured the three cutting forces, what he noticed was the diagram up right here. If he increases the depth of cut, if he kept cutting speed and feed constant but played with depth of cut, he noticed that there is a relation between depth of cut and cutting forces, and the relation is rather simple, linear. If he increases cutting forces, if he increases depth of cut, the cutting forces increase in the same relation in case of steel, because that was his basic test material. With other words, he noticed that if you increase your depth of cut by 10%, that your cutting forces increase by 10%. And if you reduce your depth of cut by 30%, your cutting forces reduce by 30%. Rather simple, straightforward. He redid the experiments with the feed and he saw the same general trend that higher feeds lead to higher cutting forces, but the relation is non-linear. If you start from low feed and you start to increase your feed in the beginning, there is a rather big impact on cutting forces, but as you continue to increase your feed, the impact on cutting forces is getting smaller and smaller and smaller. It's like the lines are curving, are flattening out. That was a second series of observations he did. If I take the two together, big depths of cut automatically leads to a conclusion that is big cutting forces. And remember the mechanics, that means big energy or a lot of energy is needed, high power is needed, and so on. Big feeds means that cutting forces increase, but not to the same extent as with big depths of cut. If you search for productivity with the high depths of cut, you need the power, you need the stability. But if you look for productivity with higher feeds, you need less that very high power and very high stability. And interesting, intriguing observation. Today we use it structural in so-called high feed machining. But that's another story. A third observation what he saw was what you see left on top. If you play with cutting speeds, a very strange behavior was observed. Low cutting speeds, you increase cutting speeds, you see cutting forces go up. If you continue to increase your cutting speed, you see cutting forces go down again. And then from a certain cutting speed on, you see that the cutting forces flatten out. Kind of that the cutting speed has no impact anymore on cutting force. There's a slight decline, but for practical reasons, not really important. The bulb there, the little hill, for a long time was a very intriguing thing, led to a lot of discussions. But in reality, it's rather simple. If your cutting speed is too low, you have a very specific phenomenon during machining, which we refer to as build-up edge, due to adhesion between workpiece material and cutting material. And if due to that adhesion a build-up edge is formed, some of the workpiece material is kind of sticking on the cutting edge, one of the effects, one of the consequences of that is that your cutting forces go up. If, however, you increase your cutting speed so that phenomenon disappears, your cutting forces go down to normal levels. So this bulb here is an indication for you that you use cutting speeds which are too low. That's all there is to this story. Further, as I said, Kinzel did tens of thousands of tests. He also evaluated the effect of geometries, what you see in the two top graphs. To the left is the cutting edge angle, to the right is the rake angle. Basically what these diagrams tells us is the sharper the tool, the lower the cutting forces, which makes sense. And he also, of course, looked into influence of wear on a cutting tool, because after a while a cutting tool is wearing out, certain wear patterns develop on a cutting edge that changes the geometry of the cutting tool, and that has consequences. In general, the picture is that if the wear increases, cutting forces go up. If the wear increases, the tool loses its original geometry, the geometry for which the tool was, or with which the tool was designed. And that impacts on how the tool functions in a negative manner. The cutting forces go up. Basically, what Kinzel came to as a conclusion was, if you have a tool, if you have a workpiece material, the highest impact, besides working conditions like wear and so on, the highest impact comes from cutting data, mainly the feet and the depth of cut, what you see unified here in one diagram. And the impact of the depth of cut horizontally considered depth of cut. And if you look to the blue line, that is the relation between depth of cut and cutting force. And you see it's a linear relation. Every change you make in depths of cut, you find back in cutting force changes. The red line represents the impact of the feet. And there you see that the impact is lower. And the bigger the feet, the bigger the difference gets between impact from depth of cut and impact from feet. Of course, that were the observations. Kinzel spent quite some time in formulating this in a certain manner so we could work with it, we could use it, which led to formulas, mathematics, calculus, where Kinzel says, depending on if you focus on the cutting force or the feed force or whatever, that the force, the certain force component is influenced by the cutting conditions, width of cut, depth of cut, and chip thickness, feed. To some extent, you have to take into consideration the geometry, and you have the material impact. The material impact, which is represented here by the K11 values, KC11, KF11, and KP11. Which refers to cutting force component, feed force component, passive force component, and stands for, and here there is some confusion, some call it a specific cutting force, others call it a specific cutting pressure, as it is a pressure, one could say. 1,1, it would be the cutting force you measure if the depth of cut is 1 millimeter and the feed is 1 millimeter. That's KC1. It's a material constant. Every material has a certain density, a certain specific cutting force, a certain strength, a certain hardness, and so on. That's the material impact. The 1 minus mc is the exponent there is a mathematical way of saying that the impact of the feed or the relation between the feed and the cutting force is nonlinear. That are the mathematics related to this process. If we look a little bit and try to see what's going on and put some order in all the data, what you see here, and I base it each time on the 6 ISO families of materials: steel, stainless steels, cast irons, non-ferrous materials, superalloys, and hard materials, you know, ISO P, MK, and so on. Or the colors, blue, yellow, red, and so on. What you see here is kind of a domain, a band, in which for the different materials you find typical KC11 values. And if we take somewhere steel as a reference material, the little white line represents kind of an average for roughly all traditional steels, respectively, stainless steels, and so on. And what we see here is that the 3 traditional ISO groups, steels, stainless steels, cast irons, are more or less on the same level. Cast iron perhaps is easier to cut, to machine. Non-ferrous materials are softer, which you see instantly represented here by a very different value for KC11. Superalloys are another story, and especially hard materials is quite another story when it comes to KC1. Remember, KC11 is an indication for cutting force, and cutting force leads us to work, energy, and power. Remember the connection lines here. MC. To which extent is the relation linear, or is approaching linear, or is going away from linear? The more the MC goes towards higher values, the lesser linearity you see in the relation. The lower, the more linearity you see in the relation. And here again you have the 6 typical workpiece materials, and you see the differences are not so big, but be careful, because these are exponents and could lead to quite big differences when you start to put values in the equation. What it means is, and that's what I try, hopefully this diagram shows it a little bit better. Again, you see the colors, green non-ferro, red cast iron, blue, yellow, stainless steels, and the orange-brown, the superalloys. What you see is that if you measure cutting forces with different ship thicknesses, call it feet, to keep it simple here, that the impact of feet on cutting forces in case of superalloys is bigger, I mean, than what you would see in case of steel, of stainless steel. The non-linearity of the relation in case of superalloys is more explicit than what you see in case of steel machining. And that's something to remember, because there are big problems with that if people are not aware of that phenomenon. Another way of showing is here, where you see it in a different way. Here you see the loads, the pressures. Previously it was forces. Here you have pressures, unified loads. You see the same phenomenon that superalloys, as an example, if you go towards smaller ship thicknesses, smaller feeds, the load is quite a lot increasing, a lot more than what we see normally in case of steel machining, which is the basic explanation why in superalloys we see situations where cutting edges are so sensitive for cracking and shipping. Yet another way of showing it, I try to show 3 times the same thing here to let you feel that playing with feeds when we talk about the mechanics of a machining process is an important thing. It's not so much the cutting speeds we focus on, it's the feeds which are important. The geometry plays, of course, a role. And Kinzel, what Kinzel measured, what we still measure today if we do the experiments, is that there are certain general relations which most of the time we bring into consideration as correction factors. Here you see a typical example where we have one situation, one material, one set of cutting conditions. We work with different geometries, and you see that cutting forces are different as geometries are different. Quite logical, I think. Next to the size, there is a direction. Cutting forces act in certain directions, which are influenced by how the cutting edge is directed or positioned compared to the cutting direction, the cutting movement, and the feed direction, the feed movement. What is important there is positioning of cutting edge line. What is important there is the cutting point and how cutting point relates to the cutting conditions. Something we have to remember, this was subject, I can go a bit fast here, at the previous session we talked about it, the dynamics of cutting forces. We think cutting forces are a stable thing. As a matter of fact, they are not, they are changing all the time. Here you see it measured and simulated at the same time, that cutting forces are not a constant value, but there is a dynamic effect. Cutting forces kind of, during machining, go up and down. There's a certain variation. That variation in smooth cutting materials, think on traditional steel, is not so big, but if you move to materials that behave in a more irregular way when it is about deformation, sharing of and so on, you see that measured cutting forces, indeed, it's not a flat line anymore, but the line starts to be curved, going up and down. You see here different types of materials. You see cast iron, you see here stainless steels, superalloys, titanium alloys. You see that materials differ in dynamics during machining. And here you have an idea about variation factors for different types of materials, just as an information. Bigger variation factors, what does it mean for us physical? Well, bigger variation factors means that from a wear perspective, we have to be more aware of phenomena of fatigue, both thermal fatigue and mechanical fatigue. That will lead to very specific wear patterns that in a lot of cases are unfavorable for us, but are very difficult to avoid due to this variation factor. Or we have to try to find solutions to minimize variation. One application where the variations are very big is milling. Milling is a situation where cutting edges are not static, but the milling cutter is turning around. That means that cutting conditions at certain points in time are different, and cutting forces are also different, meaning that it leaves, if you measure it really in detail, you see here examples of cutting forces, how during milling cutting forces are very dynamic, going up and down. That is the basics of the model. Now, if we apply it, what does it mean? Power and energy consumption. You remember power is energy per time unit, and energy is cutting force, is the thing we need to make the cutting tool work, and work is cutting force multiplied by travel distance. It's mechanics, Power, energy consumption, dynamics of the process, vibrations, workpiece quality, because you have action and reaction. The tool will potentially deform the workpiece, put it out of tolerance, and so on. Tool wear, all of those things are influenced by cutting forces. Cutting energy, you see here an intriguing thing. You see here on the horizontal axis, every point on the horizontal axis is as such, it's a combination of feet and depth of cut, but it's a combination that gives you the same metal removal rate. With other words, the same machining productivity. Yet, if you look to different points on that horizontal axis, every point corresponds with a different energy needed to do the operation. Left, you see a certain combination of big depth of cut and small feet. Right in the diagram, you see big feet and small depth of cut, but the relation is as such that there is balance, that you have the same productivity, and you see here energy consumption. Big feet combined with small depths of cut consume less energy, unified, specific energy, than the opposite. An interesting thought to take into consideration. Here you see the same thing shown in a different way. Here you see a relation between feet, cutting speed, and specific energy. And if you take feet and cutting speed now, and if you start playing with it, what you see here very, very clearly is that high feeds and high cutting speeds give you low specific cutting energy, while small feeds and small depths of cut gives you big specific energy, joules per cubic millimeter. Also here an intriguing thing to stand with. Shown this in a two-dimensional graph, this says that if you work with a small metal removal rate, one could say in this diagram, the situation to the left is finishing, the situation to the right is roughing, and the vertical axis gives you specific energy. This diagram teaches us, based on observations and some calculus, that finishing demands higher specific energy, more specific energy, than roughing. How about that as a consideration if you talk about energy-efficient machining? The background here, because people say, how is that possible? I don't understand that. Well, the background here, things that people forget is that if you look to energy consumption is not just a machining process, it's quite a lot more elements that consume energy during machining. But if you add everything up, situation by situation, you end up in the diagram you see here to the left. Cutting power. I think daily people worry about, cutting power. Do I have enough power? Will this work? But if you understand mechanics, if you know cutting forces, calculating the power you need to do an operation do not need to take more than 2 minutes, or at least to have an idea about what you talk about. Vibrations is mechanics. If you push on a tool, if the cutting force, if the force goes up and down, and remember the dynamic nature of cutting forces, there is a risk that you make the tool vibrate. Cutting forces, the tool pushes against the workpiece pushes back. That means that cutting forces will move the tool or will move the workpiece. Tool movement could lead to a certain vibration. Now the workpiece moves means that you can start to have issues with shape of workpieces, dimensions of workpieces, and so on. A big number of the wear patterns we are confronted with are based on mechanical things, cutting forces. Understand cutting forces, the physics of cutting forces during machining, and quite a lot of the wear patterns you see appearing on cutting edges, and if you don't like what you see, taking them away from a cutting edge is quite simple. It's mechanic thinking. Tool breakdown. What you see here is a nice one. Any idea what happened here? I'm very interested to hear what you think if you see this. If imagine you are confronted with this and somebody asks you, now what? What would you answer? Looking forward to see in the comments some of your feedback on this. Summary and conclusions. Cutting forces. Machining is about understanding the mechanics of the process, thermal effects, tribological effect. Today we talked about the mechanics, the cutting forces. It's a mechanical exercise. As I told you, if you want to know if you did the exercise well, if your insight was good, if your mathematics were good, check with people. People will tell you if there were vibrations, yes or no. Of course, people need to be capable of recognizing a problem as a problem. That's why well-educated people is important in this context, of course. And look at the tools. Tools will tell you a lot of things if you look at it. And there we have standardized approaches like what I refer to, for instance, GTDA. Well-balanced machining. Machining is about having balance. Today we talked about the mechanical balance. The model we use today, it's a macro model and it still gives very good results. It's referred to as the Kinzel model. It's based on empirical data, but to make it work, again, you need empirical data. You need, next to the model-based machining, sensor-based machining has to support this. I need values for KC11, I need values for MC, I need variation factors and so on. And all those data needs to be available if I want to calculate with all this. Are they the key to precision? Yes. Because if you have problems with quality, shape of a workpiece, positioning, dimensions, yeah, it's because the workpiece deformed during machining too much. When why is a workpiece deforming? Because your cutting forces were out of what was allowed. You have to reduce them or you have to change the direction in which they work. So if you have that under control, you have your key to precision. Productivity can be measured through OEE. You know OEE, and in OEE, a big loss in OEE is the so-called minor stops. And why do we have minor stops? Because there are vibrations we need to solve. Because there is a tool breakdown. Because the cutting edges break. Because workpieces vibrate. And all of those things would lead to unexpected standstill, minor stops. It's major stops, but anyway, minor stops in OEE terminology find their origin in the mechanics of the process. So if you have those under control, yeah, automatically you reduce your minor stops, and automatically you increase your OEE, you increase your productivity. If you are interested for more information, there's quite a lot of literature available on this. Just send me a message or send a message here in the comment, and we see with what we can help you. We can send you whatever you need. A copy of this presentation, of course, you can have, is available. Because I'm pretty sure here and there I went a bit fast through all the slides. Perhaps you want to look back at them and see a little bit more in detail what exactly was there. Perhaps you have questions. Don't hesitate to contact me. Think on the survey, which you will find very soon on social media, where this whole thing, about sensor-driven machining and so on. We want to know what you think about those things, how you feel about those things, because we want to develop a good way of thinking in this context. And now, before we close, let's check if there are questions from an urgent need. There is one gentleman asking if I could shed some insight on thermal shock, machining dry versus coolant. You have an hour? Because that's a little question, but a big answer. If William sends me his information, I can share with him quite a lot of information about this. But to be honest, handling it here today, I have to keep my eyes a little bit on the time also. because it's a too big subject to hassle in 10 seconds through. Okay, so let me know, and I send information. Then there is a question: what is sensor-based machining? Yeah, I know. It's a bit. Sensor-based machining is, one could say, data-driven machining. It is okay. I have machining. I understand my machining. I have model as to describe machining, but to make the models work, I need to have data. The Kinzel model is simple. Kinzel says the cutting force equals Kc11 multiplied with, and so on. Very nice. But I need to know Kc11 for different materials. Otherwise, I can't do anything with this model. I need to know my Kc11s. I need to know the exponents. I need to know the influence factor of geometries. I need to know how the impact from where is, and so on. So I need data, collecting those data and making those data the basis for taking decisions. That is what academics call sensor-based machining. I hope that clarifies it a little bit. Another question: why are superalloys so sensitive for low feeds? Yeah, indeed. A few of the diagrams I showed very clearly show that the non-linearity of the relation disappears completely at lower feeds. Superalloys have two properties that makes them kind of reacting in an allergic way to small feeds. One is strain hardening. Superalloys show a tendency, more than other materials, because every material have it, but superalloys more than other materials, to become stronger when it's being deformed. What is machining? Machining is deforming. So it could be that during machining, during the process itself, you strengthen the workpiece material, the superalloy, the surface of it, and then comes a next cutting edge. And what next cutting edge? I take milling. A milling cutter with 4 or 5 teeth. First tooth is cutting, second tooth, third teeth, fourth teeth, first teeth. So it's one cutting edge after the other. Well, it could be that the first cutting edge creates a hardened layer on the surface in which the second cutting edge tries to cut. And then you have a problem. And that's why with lower feet, with lower ship thicknesses, you end up in a situation that cutting edges only cut in strain-hardened material, and that makes that cutting forces increase very, very fast in lower feeds. That's one. The second one is that superalloys have low thermal conductivity. That means the heat which is generated during machining is not evacuated with the ships or through the workpiece material. It stays focused, concentrated on the cutting edge. Now, from a thermal perspective, what we try to do is to evacuate as much heat as possible with the ships, because the ships goes away from the process and keeps the temperature in the cutting zone rather acceptable low. Now, if you have a superalloy, you have already an issue with that, because the ships kind of do not like to take the heat away. And if on top of it you create small ships with your small feet, you have an even smaller volume of a ship that originally already didn't want to take heat away. And that means that the heat stays focused on a cutting edge, and is kind of, I'm exaggerating now, but I don't know a less heavier word than softening. It is softening the cutting edge, kind of, making it behave or deform during machining, and is influencing the cutting forces also, because kind of the geometry of the cutting edge line is changing. So there is a physical explanation why we see this phenomenon of superalloys, especially compared to more traditional materials, being kind of sensitive for low feeds, which leads to rather high relative energies, for instance, during machining. What is the minimum cutting speed to avoid build-up edges? Another question here. That is depending on workpiece material. I would say for soft aluminium, it's somewhere around 600 meters per minute. Build-up edges also will appear in hard steel. People say hard steel, yes, also in hard steel. In every material there is a tendency for build-up edges. But build-up edges in hard steel you find when your cutting speeds are below 20 meters per minute. In traditional steel, it's somewhere with modern cutting materials, with carbide, coated carbide, it's around 80, 90 meters, 70 meters per minute. So there's no one value. It's very heavily workpiece material depending. I would say it's one of the elements we build in our cutting data software. As you know, we have what we refer to as suggest and so on. It's cutting data software, and that software always will give you certain bands of cutting conditions, and that minimum cutting speed to avoid build-up edge is built in those systems. So I would say if you worry about it, follow instructions from suggest, and normally you will never end up in that dangerous zone where you have build-up edges. There are cases where it's not so easy, because it's easy for me to say here aluminium 600 meters per minute, but imagine a small milling cutter, diameter 1 millimeter, 600 meters per minute. Yeah, you need the RPM. Huh? So it's not always easy to do it, but yeah, that's where it is. Another question, is there software to calculate dynamic cutting forces, like for instance for milling? Yes, that exists. It's more software, how should I say, that simulates. It's perhaps not exactly fully correct, but it simulates, and what you can learn from the software is how big the variation factor is, which is very often what we want to know in this situation. The average value is one thing, but the variation around average, how much is it fluctuating, going up and down, that is crucial. Yeah, we have some time more. Can sharp geometries give high cutting forces? I think I understand the background is the diagram I showed, where the sharpest geometry to the right gave the biggest cutting forces. Yeah, it is possible. If you use a sharp geometry with high feeds, the ship kind of will jump over the geometry, and it's the rake phase that will kind of generate the true cutting geometry. And in modern tooling, rake phases are always negative. Nearly always negative. That means if you have a sharp geometry and you use it with a feed which is too high for that geometry, indeed you can end up in a situation where cutting forces are high and you risk to have issues with vibrations. So it's a very typical example. Normally we say if you have vibration problems, you should increase the feed. I think in 80% of the cases that's good advice. But however, there are 20% of the cases, if you look at the geometry you have and the feed you have, where better advice would be to reduce the feed. But this is a bit in the chapter of intuition-based machining, you know, and here you start seeing how it all, intuition-based, model-based, it all kind of connects to each other. Good. One last question. Where do I find KC11 and MC values? Now, that's a good question. There was a time where everybody was doing manual calculations, that you could find those tables in roughly every technical guide you could find from whoever as a supplier. We all put tables with KC11 and MC in our technical guides. As the time of manual calculations passed, and today we are more into use calculators, use software, those tables became a little bit obsolete, and we kind of removed them. And there are discussions, is that good, is that not good? There's to be said something for both. I think it would be wise if those tables in perhaps a simplified form would still be available. But on the other hand, as we suggest, it gives us the possibility to work with much more accurate KC11 and MC values. Because I said KC11 is a material constant, and that's absolutely true, but I didn't say you everything. Because KC11 being a constant value for a certain material is, however, also influenced by a number of other things. The KC11 for a positive cutting tool in a certain material will be different than the KC11 for another geometry. And the point geometry has an influence, and the wear, and there's so many things which, if we try to do it manually, it becomes impossible. If we use the computer, it's in reach. We can work with it. So in that respect, if you want to do that type of calculus, I would strongly suggest you use the software which is available. The results will be much more accurate. If, however, for some quick calculations you say, I need to know quickly in the workshop, it would be good, if some of those tables would be still available. You know what? If you want, I can send some of you that you have, at least some indications. But as I say, bear in mind that will be only usable for rough calculations. If you want to do the more accurate ones, I suggest to use the available software for that. And now it's time to stop, because I see that we already are over time. Thank you. I hope it was an interesting session. We talked about the mechanic side of machining, the cutting forces and everything that relates to it. We had two main things. One thing is the cutting forces, by what are they influenced? What do I need to know to have an idea what's going on mechanically around the cutting edge? I need to know the material, the tool, cutting conditions, and so on. And how can I work with it if I have an issue? How do I know what to modify, what to change if there is an issue with cutting forces? And the issues with cutting forces, that was the second big part in this presentation, could be I don't have power, I consume too much energy, I have vibrations, I have too much broken tools, I have broken inserts, and all of those things lead to workpieces that are, from a quality perspective, unsatisfactory, and or leads from a productivity perspective, somewhere a production manager that is unhappy because his OE is too slow. And often when you dive into that in machining production, especially small batch production, you see that it's the so-called minor stops that are the evil thing in the story. I hope it was interesting. We stop now for the end of the year. On behalf of my colleague, friends, myself, I wish you a very nice holiday season. And I'm looking forward to see you back in January next year. We have 2 consecutive sessions there, one in January, one in February, on tool holding. Tool holding technology, not to be neglected. Very often it is neglected, and that is not good, because you can have the best machine tool in the world, the best cutting tool in the world, but if they are wrongly connected to each other, you have nothing. But that's for January. Thank you very much.